Okay, so if we look at the relationship between change in entropy of a system, we can relate that to heat of a reversible process divided by temperature. Now, when we reverse a process, what do we mean by a reversible process? Well, when we reverse that process, we're going to make sure it occurs in tiny increments, right? Part of the reason for that is we want to make sure that the system remains at equilibrium. Okay. Now, the direction of the change is going to be reversed by changing very, very tiny reversal of conditions. We need to do that so that system stays at equilibrium. It also is going to help us lead to an isothermal process, which means that any change in temperature is going to be equal to zero. So we don't want to be reversing a process and changing the temperature, because delta S of the system is related to a single temperature. Okay. Now, what does this all relate to? Well, this is going to relate to something called the second law of thermodynamics. The second law of thermodynamics simply says that delta S of the universe is going to be equal to delta S of the system plus delta S of the surroundings, and that's always going to be greater than zero. Okay? So the total entropy of the universe is always going to be increasing. All right? Now, with this delta S of the universe equation, it's going to help us identify spontaneity of a process. Okay, and the reason why we need to look at this is that the sign of a delta S for any reaction doesn't predict by itself what's going to occur, whether a process is going to be spontaneous or not. Okay, what we do have to look at is that a process is going to be spontaneous in a direction that increases the entropy of the universe. So if we look at the equation above, what conditions do we need to have in order for that to occur? Well, if delta S of the system is negative, delta S of the surroundings has to be greater than that value, and it has to be a positive value, so that we end up with a delta S of the universe greater than zero. If delta S of the surroundings is negative, then delta S of the system has to be greater than that, so that we end up with a value for delta S of the universe that's greater than zero. Okay, that's the main thing. We always have to have the total entropy of the universe increasing. Okay, now when we consider the surroundings are going to function as a heat source or a heat sink. Right, and we kind of talked about this before with enthalpy. Okay, so if we look at these processes, we can go to identify whether each one of these Q's are going to be greater than, equal to, or less than zero. Okay, so for an exothermic process, and keep in mind it's exothermic with regards to the system, Q of the system then, in an exothermic process, we're going to gain heat or lose heat. Well, we're going to lose heat, which means Q of the system is going to be less than zero. If we're not in an isolated system, where is that heat going to go? It's going to go into the surroundings. So Q of the surroundings would be greater than zero. The net effect would be that the entropy, because we're putting heat into the surroundings, the entropy of the surroundings would be greater than zero. Okay? If we look at an endothermic process, for an endothermic process we have to put heat into the system, which means Q of the system is going to be positive or greater than zero. Q of the surroundings then, because it provided the heat, is going to be less than zero. Well, if we're taking heat from the surroundings and putting it into the system, then the entropy of the surroundings is going to end up being less than zero. Okay, so when looking at this delta S of the universe and those relationships we just talked about, really what we're going to look at is for any reaction, Q of the system is going to be equal to negative Q of the surroundings. Right, which means heat transferred for a specific reaction is the same regardless of the temperature of the surroundings. Okay, so we're just looking at heat transfer. All right. What that allows us to do then is we can look at a delta S of the system that's equal to Q of the system divided by temperature. If we then use that same process and think about the delta S of the system in terms of Q and T, well then delta S of the surroundings would be equal to negative Q of the system divided by T. Remember, Q of the system is equal to negative Q of the surroundings. So delta S of the surroundings would be the negative value of the Q of the system. Okay. Well, if I look at Q of the system, I can also relate that to delta H of the system, as long as I'm at a constant pressure. So delta S of the surroundings can also be equal to negative delta H of the system divided by temperature. Okay, that's going to be an important relationship, especially when we talk about free energy calculations. Now, when I look at these equations, since entropy depends on temperature, delta S of the universe is also going to be affected by the temperature at which heat is transferred. So the Q's are that heat transferring back and forth between the system and the surroundings. T is the temperature at which this occurs. So if I look at each one of these terms, what's going to happen to each term as temperature increases? Well, let's look at delta S of the system. As T goes up, what happens to delta S of the system? Delta S of the system is going to get smaller. Right? Delta S of the surroundings is going to become less negative. Right? So it's actually becoming more positive. Okay? The main thing is delta S of the universe is always going to be greater than 0. It just depends on whether delta S of the system versus delta S of the surroundings. So let's take a look at an example of this. So let's say at 298 Kelvin, we've got this formation of ammonia. It's going to have a negative delta S of the system, and that's been provided there for the equation. If we wanted to calculate delta S of the universe and determine whether a reaction occurs or not, we can actually calculate that. Okay? Now, in order for a reaction to occur, what has to be true? Well, remember, delta S of the universe has to be greater than 0 for a process to be spontaneous. So what that means is my delta S of surroundings has to be a greater positive value than 197. Because when I add my delta S of the system and delta S of the surroundings, I have to get greater than 0 for a spontaneous process. So what else do we need to know in order to calculate delta S of the universe? Well, we need to know delta S of our surroundings. So how are we going to get our delta S of our surroundings? Well, we need to calculate that. Right? If you remember, delta S of the surroundings was the negative delta H divided by T. So we need to calculate delta H of reaction. Now in chapter 6 we talked about calculating delta H of reaction from the standard molar enthalpies. So if I look up the standard molar enthalpies in the tables, I can see that ammonia is a negative 45.9 kilojoules per mole. H2 is 0 kilojoules per mole, and N2 is 0 kilojoules per mole. Okay, well then I just do my products, sum of my products minus sum of my reactants. So I end up with the delta H of reaction. That's a negative 91.8 kilojoules. Again, with my delta S of surroundings, that's equal to negative delta H of my system divided by T. So I can take my negative 91.8 kilojoules. I'm going to convert that into joules. I'm going to divide by my temperature in Kelvin, and don't forget that there's a negative out in front of all of that. So I should end up with 308 joules per Kelvin. Now why did I convert from kilojoules to joules? Well, my delta S of my system is in joules per Kelvin. I want my delta S of my surroundings to be in joules per Kelvin. You've got to make sure that the units agree. Now that I know my delta S of my surroundings, I can calculate my delta S of my universe. So I simply plug into my equation. Well, delta S of the system was a negative 197 joules per Kelvin. Delta S of the surroundings was 308 joules per Kelvin. That gives me 111 joules per Kelvin. So is this reaction going to occur as written? Is it spontaneous as written? Well, since delta S of the universe is greater than 0, the reaction is going to occur spontaneously at this temperature. Okay, that's how we can actually calculate these things out. Now we can also think about, without actually doing the math, we can also think just in terms of kind of a graphical representation of what's going on with this. So if I look at this graph here, delta S of the system is in the pink and it's a negative value. Delta S of the surroundings is green, it's a positive value, which means delta S of the universe is positive. Okay, so even though that the entropy of the system is decreasing, we have a larger increase in entropy in the surroundings, so we get a net overall increase in the universe. So simply predicting based solely upon the system doesn't predict whether we're going to have a spontaneous process or not, because we have to consider what's happening for delta S of the universe. Okay. Now, using this graphical representation, let's go through a couple more of these things. All right, so in this example here, is this process going to be endothermic or exothermic? Well, how do I know that? Well, that's where I have to look at delta H of the system. So in this case, delta H of the system is less than 0. If delta H is a negative value, it's an exothermic process. Okay. In this example, delta S of the system is a positive value. Delta S of the surroundings is a positive value. If both of those are positive, well, then delta S of the universe is always positive. Right? So this process is going to be spontaneous under any conditions. It doesn't matter what the temperature is, it's always going to be spontaneous. Right? If we look at just delta S of the surroundings, we know that that's always going to be positive because delta H of the system is negative. And the negative and the negative make that positive. Okay, let's look at another example here. Is this process endothermic or exothermic? Well, looking at delta H of the system, we can see that that's a positive value, which means this is an endothermic process. Okay. Now, in this example, we're saying delta S of the system is a positive value. Okay. Delta S of the surroundings is going to be a negative value. Why? Well, because delta H of the system is positive, and we plug that into the equation, we get a negative value for delta S of the surroundings. Okay. Now, in the graphical representation here, we see that delta S of the universe is positive, which means this process would be spontaneous. But if we look under what conditions the reaction is going to be spontaneous, well, if we go to delta S of the surroundings, if delta S of the surroundings becomes a larger negative value than delta S of the system is positive, delta S of the universe is going to become negative. So under what conditions does delta S of the surroundings get to be a larger negative value? Well, as temperature decreases, delta S of the surrounding is going to become more negative. So at low temperatures, at low enough temperatures, we may actually see where this process is no longer spontaneous, because the delta S of the surrounding becomes such a large negative that it forces delta S of the universe to be negative. Okay, let's look at another example. All right, endothermic or exothermic? Well, delta H of the system is less than 0, so it's an exothermic process. If delta H is less than 0, it's always a negative, which means delta S of the surroundings is always positive. Delta S of the system in this case is negative, so delta S of the universe is going to be positive. So what conditions is this reaction going to be spontaneous? If delta S of the surroundings becomes a smaller positive value than delta S of the system is negative, delta S of the universe is going to become negative. So under what conditions is delta S of the surroundings going to be a smaller positive value? Well, as we go to higher and higher temperatures, delta S of the surroundings is going to decrease in size. And eventually we're going to get a point where delta S of the system is more negative than delta S of the surroundings, and delta S of the universe would then be negative, and we'd no longer be spontaneous. Okay. Now, another thing we have to consider that we haven't talked about yet is a reaction that's at equilibrium. Okay, now we have to think about what happens at equilibrium in a reaction. So looking at this reaction of A plus B going to AB, what we mean by equilibrium is that the forward reaction can occur, A plus B going to AB, but the reverse reaction could occur as well. All right, AB can go to B plus A. Now really, when these things are at equilibrium, net overall, neither the forward nor the reverse reaction is going to be spontaneous. They're both occurring at the same time technically, so they're canceling each other out. Now, for any process that's approaching equilibrium that hasn't gotten to equilibrium yet, delta universe always still has to be greater than 0. Okay, but what happens when we're finally at equilibrium with respect to entropy? Well, we're going to see no net change. In other words, delta S of the system is going to be equal to negative delta S of the surroundings. So what does delta S of the universe equal then? It equals 0. So when delta S of the universe is 0, we're at true equilibrium. Okay. So let's talk about the third law of thermo. It's the last law we're going to deal with. Third law says basically the entropy of a system is going to be equal to 0 at 0 Kelvin. In other words, if we have a perfect crystal, we're going to have 0 entropy at absolute 0. What this means is with a perfect crystal, we have a flawless alignment of all its particles. Because we're at absolute 0, we have the minimal amount of energy. So the reality is we truly only have one microstate. When we plug that one microstate into the equation, S equals K natural log of W, well, W would be 1, natural log of 1 is 0, so S overall is 0. Okay, that's what the third law of thermo says. All right, so up to this point we talked about general predictions of entropy. We talked about how to calculate entropies using values of Q and T and delta H. All right, now we're going to talk about calculating entropy based upon standard molar entropies. Okay, and this is something similar to what you did with the delta H of reactions. We're just not going to talk about delta S of reactions. We're going to take the sum of the products minus the sum of the reactants. Okay. Now, when we're dealing with standard molar entropies, S naught is for standard state of the substance, right? Entropy at its standard state, that little knot represents that. Okay, the units are going to be joules per mole Kelvin, right? And under a standard state, when dealing with the entropy, we're going to have 1 atmosphere for gases, we're going to have 1 molar for solutions, and any pure substance is in its most stable form for solids and liquids. Okay, you need to remember also, don't forget that delta H of reaction is equal to sum of the products minus sum of the reactants. That knot represents the standard conditions. Okay, so let's look at an example of this calculation. We're going to predict the sign of delta S of reaction and calculate its value. Okay, so we're looking at the combustion of 1 mole of propane at 25 degrees Celsius. But in order to calculate a delta S of reaction, we need to know what the products are and what the reactants are. So we need a balanced equation. All right, now it's a combustion reaction, which means we're going to take our compound, add it to O2, form CO2 and water. All right, once we get those balanced equation, we then need to look up our standard molar entropies. Now, where are we going to find our standard molar entropies? Well, that's going to be a table you're either going to be given, or it's in the back of your book or into your book in one of the appendices. Okay. This particular table is going to have delta H values, delta G values, and S values. Okay. If we look at the C3H8 gas, we end up with 269.9 joules per mole Kelvin. It's important you note you may have a same formula, but different phases are going to have different values of entropy. Right? If you look at water in the gas phase, it's 188.72. Water in the liquid phase is 69.940. Remember, entropy is dependent upon phases. You've got to pay attention to the phases. Okay. So O2 gas is 205.0 joules per mole Kelvin. CO2 gas is 213.7. And H2O gas is 188.72. Remember, we're looking at the gas, not the liquid. It depends on what the equation says. In this case, I have it going to gaseous water. Okay, so let's run this calculation. So we've got our formula. We know that we're going to do sum of the products minus sum of the reactants. So our delta S naught of reaction, we'll take 3 moles times the value for the CO2 plus 4 moles times the value for the H2O, add those two together, subtract out 1 mole times the value for the C3H8 plus 5 moles times the value for the O2, add those together, right, and do products minus reactant. When we do that, we get a delta S naught of reaction of 100.98 joules per Kelvin. Okay, well, if delta S of reaction is positive, based upon entropy alone, we're increasing entropy, so we'd expect, just based upon entropy alone, we'd expect this reaction to be spontaneous. Okay, and that's how we're going to calculate delta S of reaction from standard molar entropies. Okay, it's similar to what we did for standard molar enthalpies. Okay, so that's the end of what we're going to talk about in terms of entropies.